In this video, we talk about double integrals using polar coordinates. Just let me do a reminder first on polar coordinates. So reminder on polar coordinates. Polar coordinates, as you know, is something that is discussed in more elementary courses, like in this college. It is taught and learned in pre-calculus. It's part of pre-calculus. Let me make a reminder of polar coordinates before talking about double integrals using polar coordinates. As you know, in polar coordinates, a point is denoted by two things. One is the distance from the origin. So if this point P has a distance of r from the origin, and it makes an angle of theta with the positive direction of x-axis. In the polar coordinates, it's denoted by r and theta. But of course, in the rectangular coordinates, the one that is more common, we denote this by x and y. And as you know, x and y can be written in terms of r and theta and vice versa. In particular here, for this discussion, we would like to see that what is x and y in terms of r and theta. Again, as a reminder, x is r cosine of theta, and y is r sine of theta. And using polar coordinates, it's easier to describe regions which look round. For instance, those regions that are part of a circle. For example, if I have a region like R, and the region R, this is an example, in the polar coordinates is all the R and thetas, such that R is from 0 to 2, and the theta is from 0 to pi over 4. If I want to show this region, this means all the points whose distance from the origin is somewhere from 0 to 2, and when I connect the point to the origin, the angle it makes is somewhere from 0 to pi over 4. That region will be this region that I'm gonna shade in this coordinate system. First of all, let me draw the circle of radius 2. So this is 2 minus 2 minus 2 and 2. So this is a circle of radius 2. All the points in this circle or inside this circle, so a better name instead of circle would be a disk because it contains also the points inside the circle. The points inside the whole disk, the entire disk, that is its boundary is that circle around this. So all the points on the circle and inside the circle, which forms a disk, will satisfy our the distance is from 0 to 2. But here I also have some other condition. The theta, the angle must be from 0 to pi over 4. So if I draw a line here that the angle is pi over 4. So the region that you see have been described up there consists of this shaded region. So every point in this region, in this slice of the circle, satisfies both of these two. The distance is from 0 to 2. It is inside the disk of radius 2. And the angle it makes is from 0 to pi over 4. Let me do another example. Suppose the region R that I have consists of all the R and thetas, such that in the previous example, R was running from 0 to 2. But suppose R runs between two values, two positive values. Suppose R runs from 1 to 3. Also, the angle runs from minus pi over 6 to positive pi over 6. As you know, pi over 6 is 30 degrees. So let's specify the region. Again, I would suggest that you try this on your own before I write the solution. So the distance of the points must be from 1 to 3. So just for now, focus on this condition. All the points in the plane whose distance is more than or equal to 1, less than or equal to 3. It's the region between two circles. Let me draw the circle of radius 1, like this circle, and the circle of radius 3. Circle like this. So that R between 1 and 3 is the region that you see is bounded by between these two circles. But I don't want all of it. I want those who make also an angle from minus pi over 6 to pi over 6. Suppose this line makes an angle of pi over 6 or 30 degrees. Let me show the angle here because I want to shade the region. So this is pi over 6 and minus pi over 6. This is the angle of minus pi over 6. From trigonometry, you know that the positive direction for angles is counterclockwise and the negative direction is clockwise. Okay, now what is that region that for all the points in that region, R is from 1 to 3, and the angle is from minus pi over 6 to pi over 6. Let me shade that. So it consists of this region here. It is the region trapped between these two circles and also trapped between those two lines. So in polar coordinates, I was able to describe this region. It's all the points consisting of R and thetas, that R is from 1 to 3 and between 1 and 3. And also theta is between minus pi over 6 and pi over 6. If I wanted to describe the region in the XY coordinates, it would have been a little bit more complicated. In fact, for the region like this, it's easier to describe it in the polar coordinates. Now let's see how this is helpful in double integrals. So in double integrals that we are integrating over some region R of some function f of x and y, instead of dx dy, just let me write dA, the infinitesimal of the area. And when we used a rectangular system, it was dx dy, or depending on which integral is with respect to x, interior or the interior or outer integral, inside integral or outside integral. Sometimes we had dx dy, sometimes dy dx, so or this. In the regions that we have considered so far, they were either rectangular regions and sometimes general regions, meaning that, for instance, x was running from a number to a number and y was between two functions of x, as we did in the previous lesson. But what if R is part of a circle, or in general, it's a round region? Then if we have this situation, it's very helpful to use polar coordinates, because rectangular coordinates in some cases would be very complicated and we need to use polar coordinates. But what we should be aware of, in the polar coordinates, this infinitesimal area, so in polar coordinates, this infinitesimal area would be polar coordinates. This infinitesimal area dA is going to be replaced by r dr d theta. It's not just dr d theta, it is r dr d theta. So when we do the double integrals in polar coordinates, that dA, that in the case of rectangular was dx dy or dy dx, depending on what was the interior integral, what was the outer integral, is replaced by r dr d theta. And of course, if the function is just given in terms of x and y, I should replace x and y, x by r cosine of theta, and y is r sine theta. So x is r cosine of theta, and y is r sine theta. Let's do an example. So now we can do the double integrals using polar coordinates if the region is a round region, like part of a circle. For example, suppose I want to evaluate the double integral over some region R, and the function is 8xy. I want to evaluate this, but I should describe what the region is, where R is the following region. R is the region consisting of all the R and the thetas. such that r is between 2 and 3, and theta is from 0 to pi over 2. Obviously, the region we are integrating over is between two circles. R equals to, like this circle. R equals 3 is this circle. The radius equals 3. And so it is between these two. And the angle is from 0 to pi over 2. So the region we are integrating over, as you can easily see that it is this region. The angle is between 0 and pi over 2, and the distance from the origin is from 2 to 3. So I'm integrating over this. In other words, if this is a function z or f of x and y, in the three-dimensional space, I'm computing the volume of the solid, which is above that region and below the surface of z equals 8xy. Okay, but our purpose here is to calculate this. So the integral 8, x is what? X is r cosine of theta. This is x. What is y? R sine theta. What is dA, or infinitesimal area in the polar coordinates? It is r dr d theta. How can I set up the limits of the integral? For the inside integral, I can use r. R runs from 2 to 3, and the angle runs from 0 to pi over 2. So I should calculate this double integral. First, let me focus on the inside the integral, which is the interior integral, this integral. So for this integral, I can pull out the constants. With respect to r, 8 is a constant, cosine of theta is a constant, and sine of theta is a constant. So let me continue on the next page. So the outer integral from 0 to pi over 2. Eight cosine theta, sine theta will be here, and d theta. And inside integral was the integral that we have here. R times r times r is going to be r cubed. So it's r cubed dr. The integral from where to where? From 2 to 3. In the region, r runs from 2 to 3. R cubed dr. Okay, now let's find this integral. This is easy, like a calculus 1 question. Antiderivative is r to the 4 over 4. It should be evaluated at these endpoints, and then we do the subtraction. 3 to the power of 4, ad1, 4 minus 2 to the power of 4, 16 over 4, which is 65 over 4. So it's that is 65 over 4. This 65 over 4 is a constant for the next integral, so I can pull it out completely. 65 over 4 comes out for the outer integral. Also, that 8 is a constant. I can pull out that 8. I mean this 8 right here. I can pull out that 8 as well. So it's 64 over 4 times 8 all come out of the integral. So the outer integral, which runs from 0 to pi over 2, is integral of cosine theta sine theta d theta. Okay, we can do this integral in different ways. One way, as you know from trigonometry, cosine theta times sine theta. This is one of the identities that you learn in like things like pre-calculus, and you have used that in probably Calc 1 and 2. It is 1/2 sine of 2 theta. As you know, sine of 2 theta is 2 sine theta cosine theta, or 2 cosine theta sine theta. So cosine theta sine theta is going to be 1/2 sine 2 theta. So far I have 60 here. I should make a correction. This was 65 over 4, sorry. So I have 65 over 4 times 8. This 1/2 also can come out times 1/2. And the integral from 0 to pi over 2 sine of 2 theta d theta. Here, then these numbers, 8 over 4 times 2, it's 8 over 8. They cancel out. So I just have 65 out of this integral. And let's calculate this integral. As you know, antiderivative of sine of k theta is -1 over k cosine of k theta. Like in this case, antiderivative is -1/2 cosine of 2 theta. You have definitely seen this in calculus 2. So then it should be evaluated at those values, and we should do the subtraction. At pi over 2, I have -1/2 cosine of 2 times pi over 2. 2 times pi over 2 is pi, and cosine of pi is -1. At 0, -1/2 cosine of 2 times 0, and cosine of 0 is 1. So just times 1. And this is going to be +1/2, another +1/2. So they just add up to 1. So this integral is just 1. So what's the final answer to this question? It is just 65. Okay, let's do another example. Again, as usual, please try to do the next example on your own before you watch the solution. So I want to evaluate the double integral over some region R. The function is e to the power of -x squared minus y squared and dA. And the region that we are talking about is the region R. sometimes R is described in X and Y, and we change it to the polar description. So it's all the xy's such that x squared plus y squared is less than or equal to 36. So before doing the integral, let's see why we want to do it using the polar coordinates. The reason is x squared plus y squared equals 36 is a circle of radius 6, right? When I have x squared plus y squared equals 36, this is the equation of a circle of radius 6. But less than or equal to 36 is the description for the disk on the circle and inside the circle. So in fact, the region that I have described by this is this region. Suppose this is a circle of radius 6. So this circle is x squared plus y squared equals 36. Less than or equal means I should consider also inside the circle. And I have no other restriction, so it is the entire circle, the entire disk. So the disk of radius 6 is the region we want to integrating over. How can I describe this in the polar coordinates? Of course, R runs from 0 to 6. And theta is from 0 to 2 pi. One full round. So theta runs from 0 to 2 pi because I didn't specify which slice of this disk. So I should consider the entire disk. So from 0 to 2 pi. And the disk itself is described as R more than or equal to 0, less than or equal to 6. Now let's try to do the integral. So R runs from 0 to 6, theta from 0 to 2 pi. That's dA is R dr d theta. And the function e to the power of, if you want, you can factor that negative out, minus x squared plus y squared. X is r cosine theta, so this is r squared cosine squared of theta. I need a bigger parentheses. And plus y is r sine theta, so this is r squared sine squared of theta. Please pay attention that I factor that negative out. Between these two terms, r squared is in common. I can factor that out. And cosine squared plus sine squared is 1. So the whole this parentheses is just r squared. Again, if I factor r squared out, I will have r squared times cosine squared plus sine squared. But from trigonometry, we know that cosine squared plus sine squared is 1. So let me rewrite this one more time. Again, I need more space, so let me continue this on the next page. So we are doing the integral from 0 to 2 pi. That is where the angle changes. And the distance from the origin is from 0 to 6. It is e to the power of negative r squared minus r squared. And for that dA, we had r dr d theta. R dr d theta. Excuse me. So first we need to do the interior integral. That's not complicated. Just for clarification, let me do it separately here. The integral of E2. To do this, I can use a substitution. The substitution that we use for this this is something similar things you have seen in Calc 2, minus r squared, and the derivative of u with respect to r is minus 2r. So du is minus 2r dr. But here I have r dr. So this is, I let u be minus r squared. But r dr is not du. Minus 2r dr is du. So if I divide both sides by minus 2, du over minus 2 is r dr. So r dr is the same as du over minus 2. So this integral is going to be equal to integral of eu du over minus 2. Over minus 2 is like minus 1/2 coming out of the integral. So I will have eu du. Antiderivative of e to the u is e to the u. There is a plus c in general for the indefinite integral, but since I need this for that definite integral, the interior integral, I don't need to worry about plus c. And this equals back substitution. U is minus r squared minus like this. By back substitution, I replace back u with minus r squared. So for the inside integral here, but with this work, the antiderivative is minus 1/2 e to the power of minus r squared. Then it should be evaluated at these numbers, meaning that this value here at 6 minus at 0. At 6, it's minus 1/2 e to the power of 6 squared is 36, and there is a negative before that, minus 36. At 0, I have minus 1/2 e to the power of minus 0 squared, which is e to the power of 0, which is 1. So what is this? This is, the first term is just minus 1/2 e to the power of minus 36. Negative times negative makes it positive, plus 1/2. So that's the value of the inside integral. So minus 1/2 e to the power of minus 36 plus 1/2. Now we get to the outer integral. For the outer integral, this value is a constant, so I can bring that out. And the outer integral is the integral from 0 to 2 pi of d theta. So what function should I find antiderivative? In fact, that function is 1. I don't see anything before d theta, so by default that is 1. Antiderivative of 1 with respect to theta is theta, and it should be evaluated at these and the numbers. Excuse me. At 2 pi, when theta is 2 pi, it's just 2 pi. When theta is 0, it's just 0, so it is 2 pi. So the final answer is the product of that parentheses and 2 pi. So it's going to be 2 pi times that parentheses. What was that parentheses? Minus 1/2 e to the power of minus 36 plus 1/2. And here, the exact value was meant. So I can't do anything about e to the power of minus 36. The only thing I can do is I can distribute these 2 over the parentheses. And so the final answer will be pi times negative e to the power of minus 36 plus 1. So we started from here. We described the region in the using polar coordinates. Then using x equals r cosine theta and y equals r sine theta, we wrote everything in terms of r and theta. And we calculated the interior integral and then the outer integral. And we came up with this value right here. Another example. Again, please try to do it on your own before watching my solution. So I want to find the integral over some region R of this function, the radical of 100 minus x squared minus y squared. And the region that we are considering the integration is the region R consisting of, this region is a little bit different from the previous one. It's still inside a disk, but not the entire disk. So the disk is x squared plus y squared is less than or equal 81. But we have an extra condition. X and y both must be positive. So x squared plus y squared is less than or equal to 81 is a disk of radius 9, right? Because radical 81 is 9. So if I want to have it for doing the double integral, if you want to have a more clear picture of the disk, if this is a circle of radius 9, the disk is inside this circle. But do we need all of the parts or no? Only those parts that x and y are both positive, the first quadrant. So we don't need we should eliminate the second, third, and fourth quadrants. So we just have a quarter of that disk in this example. In the previous example, there was no condition like that x and y must be positive. So that's why all the 4 quarters of the disk were considered. But here, just the first quadrant, so the first quarter of the disk is meant. How can I describe this in terms of the polar coordinates? So this part inside the disk easily described as r rounds from 0 to 9, because the distance from the origin is less than or equal to 9, so it's from 0 to 9. X and y positive means that the angle that we make, or the points when connecting to the origin make with the positive direction of x-axis, it cannot be beyond pi over 2. So theta is between 0 and pi over 2. In the previous example, theta runs from 0 to 2 pi because the entire disk was meant. There was no condition on the sign of x and y. But here, x and y must be positive. So all the points should be in the first quadrant, meaning that on all the points in the first quadrant, when connected to the origin, the angle that they make with the positive direction of x-axis is the angle is somewhere from 0 to pi over 2. So when I set up this integral, it's going to be the integral theta runs from 0 to pi over 2. R runs from 0 to 9. And I have 100 minus x is r cosine theta. So x squared is r squared cosine squared of theta. Y is r sine theta. So y squared is r squared sine squared of theta. And dA, if you wouldn't mind, let me erase this. And dA for the polar coordinates is going to be r dr d theta. Let me write that back here. The theta is from 0 to pi over 2. So this is the integral that we need to take care of. Just as a reminder, similar to the previous example, if I factor minus r squared between these two terms, if I factor minus r squared out, cosine squared plus sine squared is 1. So this is just minus r squared. Or in other words, 100 under the radical, I have 100 minus r squared. So let me continue on the next page. So theta runs from 0 to pi over 2. R runs from 0 to 9. Radical of 100 minus r squared. R dr d theta. Again, I need to take care of the inside integral. In other words, we should find the antiderivative of 100 minus r squared r dr. Using a substitution, u equals 100 minus r squared. We can do this. This is a kind of Calc 2, or even it could be a problem in Calc 1 problem that you take u to be 100 minus r squared and find antiderivative. If you do it correctly and simplify, so let me skip that step. At the end, by using substitution, the antiderivative of this function is going to be minus 1/3 100 minus r squared raised to the power of 3/2. Of course, for the indefinite integral, we have a plus c, but since we need this for a definite integral purpose, we don't need to worry about that. So this evaluation of this minus 1/3 100 minus r squared to the power of 3/2 evaluated at these two numbers. So let's calculate this. I should evaluate at 9, then minus the evaluation at 0. At 9, minus 1/3. 100 minus 9 squared. 100 minus 81, which is 19. 19 to the power of 3/2. So 1/3 times 19 to the power of 3/2. At 0, that's easier. 100 minus 0 is just 100. So I have minus 1/3 times 100 to the power of 3/2. And I want an exact answer, so I don't use estimated decimals. Let's see what number it is here. So the first number is minus 1/3, 19 to the power of 3/2. So as you know, using basic algebra, it is like 19 times radical 19. A number to the power of 3 halves means the number times the radical itself. Minus minus is plus. 1/3. 100 to the power of 3 halves. 100 to the power of 1 half, or radical 100, is 10, and 10 cubed is 1000. Okay, so this number is a constant for the outer integral, and that can be pulled out. So let me continue next page. So what I have here is it equals that number minus 1/3, 19 radical 19 plus 1/3 times 1000. And the integral that we had, the integral was running, the outer integral, theta was running from 0 to pi over 2. The integral from 0 to pi over 2 d theta. Again, I don't see any function in terms of theta, so that means it is 1 here. Antiderivative of 1 is theta. It should be evaluated at this endpoint. At pi over 2 is pi over 2. At 0 is 0, so it is just pi over 2. So the final answer is pi over 2 times this number here. But these two terms have 1/3 in common. I can pull that out, and 1/3 times pi over 2 makes it pi over 6. So that pi over 6 is coming from pi over 2 times 1/3. Inside the parentheses, 19 radical 19, and then plus 1000.